exactly did China discover on the moon that suddenly drove major powers to rush back to lunar landings? The last time humans set foot on the moon was back in the last century. After that, entire generations barely cared about the moon anymore. Everyone's attention drifted towards Mars, Jupiter, and deeper destinations farther away. But then, in just the past 10 years, everything reversed. New rockets launched one after another. New lunar programs rushed onto official schedules. And here's the wild part. No one is focused on stepping on the moon anymore. They are focused on claiming resource sites. So the real question is no longer, can we still land on the moon? But rather, what new things have appeared on the moon that are now worth restarting a race we paused for decades? To answer that, we need to lay out our own strategy first. Many people don't know this. China didn't seriously and systematically target the moon until the 21st century. We started late, so in the beginning, we were extremely restrained, focusing on one mission, reconnaissance first. Step 1 was Chang 1. Its job was simple yet critical: orbiting the moon, map every rise and fall of the lunar surface, and build a 3D topographic atlas. Mark every crater, mark every highland. Meanwhile, scanning lunar soil composition, identify what elements exist inside that gray dust. Where is it just ordinary dirt? Where might something worth attention be hiding? And inside that first batch of data, the signal for Helium-3 was identified clearly for the first time. A substance extremely rare on Earth was suddenly showing measurable traces in moon soil. Nobody dared claim we had found a new oil field, but one fact became clear. That gray layer on the moon, the one that looks the same everywhere, is not the same everywhere. Some areas are just crushed rocks. Some areas may sit at the center of future global energy maps. But knowing where something looks promising is nowhere near enough. If we want to upgrade from orbiting overhead to actually landing hardware, a new core question appears. Is it safe to put a spacecraft down there? So after Chang 1 finished the terrain survey, step 2 was Chang 2. Its mission revolved around one problem: pick safe landing zones for future missions. It lowered its orbit, upgraded cameras, scanned candidates' landing regions over and over again. Where are giant boulders? Where are the invisible slopes? Where are crater clusters so dense that drifting a few hundred meters would destroy a lander? All of those details had to be mapped beforehand. After countless passes, we finally built a reliable landing safety list. We knew which places were safe to touch down, which places were absolutely do not touch. With that list, step 3 became possible. The real leap, Chang 3. No more staring from far away. This time, we had to run the full landing pipeline: deceleration, hovering, hazard avoidance, soft landing, executed for real on lunar soil. And in the end, the lander touched down calmly on the chosen flat. No tilt, no slide. That moment meant China possessed the ability to stand safely on the moon. Then the U2 rover rolled down its ramp and began to roam, proving another truth: a rover could survive low gravity, massive temperature swings, and intense radiation, not just snap a few photos and die. More importantly, its ultraviolet telescope lifted toward deep space, giving humanity an entirely new vantage: a space observatory from the lunar surface. At that point, our dataset shifted from a flat map into a 3D dossier: potential resources, verified landing zones, and a complete technical chain capable of soft landing and working on the ground. But reaching that level pushed us towards a new question. If the near side works, what about the far side? The side that never faces Earth? The mission that wrote that question into its paperwork was Chang 4. Because once you target the far side, difficulty jumps to another league. The near side is always visible. Earth can always send signals. If something breaks, you improvise. The far side is different. It faces outer space forever. Every command you send gets blocked by the moon itself. You can't even transmit the words. We arrived, which means, if even one link of that tech chain fails, your entire spacecraft could disappear silently, outside human sight. So why take the risk? 2 reasons: silence and geology. First, silence. The lunar far side is shielded completely from Earth's radio noise. Raise an antenna there, and you hear the true voice of the universe. Astronomers have dreamed of this for decades. The second reason: primitive crust. Those dark Mars plains on the near side are volcanic resurfacing. The far side crust is thicker, more heavily cratered, preserving much older history. Whoever lands there first gets unprecedented first-hand data. And so, Chang 3's core purpose was brutally directed. Dare we operate blind on the far side of the moon and secure our own sample set? To do that, the first step wasn't a lander, it was a bridge. Before Chang 4 was launched, China launched a relay satellite into a special point beyond the moon. From that vantage, it always sees Earth and the lunar far side simultaneously. Ground commands go to the relay. The relay bounces them to the rover. Pictures and data climb back through the same bridge. Once the bridge was steady, Chang 4 began its descent, aiming for the South Pole Aitken Basin, inside Von Kármán crater. On January 3, 2019, it touched down smoothly, on land no human machine had ever reached. Hours later, Yutu-2 rolled out. For the first time in history, humanity was no longer orbiting the far side, but surveying it from the ground. From that moment on, our image of the moon changed. This was a world with barely any air, a world with thicker crusts, uncountable craters, harsh, rugged terrain. Scientists stared at those images with one burning question: how can one moon have 2 dramatically different faces? Yutu-2's mission became this: driving across unfamiliar gray ground, measuring, imaging, computing, push that asymmetry mystery forward. Later, online stories begin circulating. Mysteries, anomalies, strange discoveries, including the viral gel-like substance. Let's clear that up. While patrolling, Yutu-2 passed a small crater. Inside, operators spotted something unusual. It was darker, shinier, with a texture unlike the surrounding dust, like a smear of melted material. Naturally, everyone thought the same thing. Something high energy happened here. Extreme heat, or a vicious impact. But because the info was released slowly, one vague sentence first, speculation exploded worldwide. Chinese forums guessed, Western forums guessed, volcanic glass, impact melting, alien artifact. But when images and spectrometry finally came out, the conclusion was simple: impact melt breccia, a high-energy strike melted soil and rock, cooling rapidly into a welded glassy mass, rich in olivines and pyroxene. No aliens, just geology. But the significance isn't the gel, it's the injury report of the far side. This site suffered a major impact, preserved fresh melted rock, and unlike Apollo samples, this was retrieved from a whole new location, a crucial puzzle piece for reconstructing lunar evolution. And beyond rocks, one tiny detail touched people emotionally. Inside a sealed metal canister, on a world with no air and brutal temperature swings, a seed sprouted from Earth. That seed lived through a complete biological test. On the moon, it grew a green shot, under controlled lighting, heat, and humidity. For a few days, a microscopic greenhouse from Earth stayed alive on the moon. The lunar night ended it. Temperatures plunged, the biological system shuts down, and everything froze. Cruel, yes, but scientifically, enough to prove, given light and heat, life can sprout on the moon. To keep it alive long term, you need heating, shielding, resources. Meaning, future lunar farming is not fantasy, it's engineering. Because of these results, scientists worldwide stopped treating Chang 4 as a curiosity and started watching it like a blueprint. Why? Because the key messages were: the far side can be reached, hardware can survive, experiments can be executed, China wasn't just getting there, it was capable of working there. Only after that did nations fixate on second-level questions: geology, radiation, resources, relay the infrastructure. The real prize wasn't memes. It was proof of capability, and capability leads to resources. So what's the biggest prize? At the top of every economic list, Helium-3. It's just a special isotope of helium, extremely scarce on Earth, accumulated on the moon over billions of years of solar wind exposure. If humanity develops fusion, Helium-3 may become a low-waste, high-efficiency fuel with energy density that humiliates fossil fuels. A few dozen grams could rival thousands of tons of coal. Estimates suggest millions of tons of Helium-3 may exist trapped in lunar regolith. In theory, enough to power Earth for thousands, even 10,000 years. That's why the spreadsheets started shaking. And when Chang 5 returned samples, scientists confirmed a brand new lunar mineral containing Helium-3. For the first time ever, Helium-3 wasn't a spectral hint. It was material in human hands. Meanwhile, orbiters and rovers were mappings where concentrations ran high or low, creating a Helium-3 distribution map. Some missions heated lunar soil to test extraction temperatures for future mining. Of course, reality check. Fusion reactors aren't commercial yet. Lunar mining is decades away. This isn't next year's industry. It's a multi-decade geopolitical game. And because it's long-term, everyone knows whoever stakes the mining sites early and matures the tech chain will own the initiative. Helium-3 is only one of the ledgers in line. To live on the moon, we need other fundamentals: water, oxygen, fuel, logistics, which shifts attention from rare isotopes to something more immediate: water ice. Water determines habitation, not theory. Tomorrow, radar, impact tests, and spectroscopy have repeatedly detected water signals in permanently shadowed craters at the poles. Hydrogen spikes, volatile lofting, ice grains. A consensus emerged: the lunar poles, especially shadowed craters, likely contain significant ice, meaning water wouldn't have to be shipped from Earth. It could be mined locally. And water has three identities: drinkable, life support, electrolysis into oxygen and hydrogen, breathable plus fuel, and circulation with solar power for semi-closed life support loops. If those three steps work, lunar resupply shifts from total dependencies towards partial self-support. China saw this early. Future missions shifted toward the South Pole. Orbiters skin temperature, reflectivity, hydrogen. Landers and rovers will sample ice directly. Depth, purity, granularity. Even Chang 5 samples from mid-latitudes showed water-related signals, meaning the moon isn't bone dry. It retains water molecules under solar bombardment. Put all that together, our logic transformed. A lunar base is no longer imagination. It's a scheduling problem. When, where, and with what tech? Especially the South Pole. If sunlight-rich ridges lie near shadowed ice pits, they become prime real estate for humanity's first persistent lunar outposts. And once the target becomes outposts, the problem shifts. Not can we reach the moon, but what's our step-by-step path to permanence? So the Chang roadmap unfolds. Chang 5 samples returned from a young volcanic plain. Results showed 2 billion-year-old rocks, younger than Apollo samples, meaning the moon was volcanically active longer than assumed. A key safety clue for building bases. Chang 6 samples returned from the far side. Core drilling. Nearly 2 kilograms of regolith and rock returned. Now spectral maps can be calibrated against physical samples. Chang 7. Go to the South Pole, hunt ice. Use a lander, rover, and maybe a hopping probe to descend into shadowed pits. Answer concrete questions. Where is the ice? How deep? Layered or granular? Is the ridge flat enough for solar farms? Chang 8 prototype inside a resource utilization 3D printing structures from regolith. Build simple construction on site. In short, Chang 5 and -6. Know the moon. Chang 7. Find the water. Chang 8. Build the infrastructure. Follow that. And by the 2030s, a Chinese-led lunar research station could sit at the South Pole. Lights on, instruments running, rotating crews. Not a flag, a foothold. But once humans lived there, the issue expands beyond China. NASA's Artemis program targets the same South Pole. Its goal mirrors ours. Not another footprint, but an outpost. Infrastructure for sustained presence. Commercial companies involved. Partner nations aligned. Originally planning crewed landings early this decade, now delayed towards the late 2020s, which places it extremely close to China's 2030 crewed landing target. 1 generation, 2 programs, 1 set of resource zones. Official Chinese planning maps even show this future. 2 operational systems coexisting at the South Pole, 1 led by China with partners, 1 led by Artemis countries, possibly not far apart, both eyeing the same optimal patches. Sun-drenched ridges for power, shadowed craters for ice. This new lunar race is nothing like Apollo. That was a sprint for footprints. This is a decades-long marathon for infrastructure. Who soft lands first matters, but who stays and controls the resource logistics matters more. And beneath polite language, cooperation, peaceful use, open access, you can feel the tension. Who establishes crewed operations first? Who completes a functioning base first? The winner shapes mining frameworks, operational safety zones, and maybe de facto lunar rules. Which raises the uncomfortable question: who owns the moon? The Outer Space Treaty states clearly, no nation may claim celestial territory. Activities should benefit all mankind. Great on paper, but the treaty never imagined Helium-3 mining, polar ice extraction, or permanent bases. It says nothing practical about ownership of extracted resources. Thus, 2 emerging rule systems appear. 1. The Artemis Accords, supporting resource utilization, allowing safety zones. Critics fear it means first come, first served in practice. The other, International Lunar Research Station, aims for shared infrastructure, shared access, but reality remains. Who pays more, risks more, and builds more, holds said more. So no one will ever say, we are claiming the moon, because the treaty forbids it. But whoever installs solar farms on the sunniest ridge, whoever builds roads besides the ice pits, will quietly control the most strategic ground. Not the whole moon, just the irreplaceable golden plots that enables power, water, fuel, and expansion. These locations are scarce, and they determined who can stay longest, operating cheapest, and scale fastest. Chang 8 prototype inside a resource utilization. 3D printing structures from regolith. Build simple construction on site. In short, Chang 5 and -6. Know the moon. Chang 7. Find the water. Chang 8. Build the infrastructure. Follow that. And by the 2030s, a Chinese-led lunar research station could sit at the South Pole. Lights on, instruments running, rotating crews. Not a flag, a foothold. But once humans lived there, the issue expands beyond China. NASA's Artemis program targets the same South Pole. Its goal mirrors ours. Not another footprint, but an outpost. Infrastructure for sustained presence. Commercial companies involved. Partner nations aligned. Originally planning crewed landings early this decade, now delayed towards the late 2020s, which places it extremely close to China's 2030 crewed landing target. 1 generation, 2 programs, 1 set of resource zones. Official Chinese planning maps even show this future. 2 operational systems coexisting at the South Pole, 1 led by China with partners, 1 led by Artemis countries, possibly not far apart, both eyeing the same optimal patches. Sun-drenched ridges for power, shadowed craters for ice. This new lunar race is nothing like Apollo. That was a sprint for footprints. This is a decades-long marathon for infrastructure. Who soft lands first matters, but who stays and controls the resource logistics matters more. And beneath polite language, cooperation, peaceful use, open access, you can feel the tension. Who establishes crude operations first? Who completes a functioning base first? The winner shapes mining frameworks, operational safety zones, and maybe de facto lunar rules. Which raises the uncomfortable question: who owns the moon? The Outer Space Treaty states clearly, no nation may claim celestial territory. Activities should benefit all mankind. Great on paper, but the treaty never imagined Helium-3 mining, polar ice extraction, or permanent bases. It says nothing practical about ownership of extracted resources. Thus, two emerging rule systems appear. One, the Artemis Accords, supporting resource utilization, allowing safety zones. Critics fear it means first come, first served in practice. The other, International Lunar Research Station, aims for shared infrastructure, shared access, but reality remains. Who pays more, risks more, and builds more, holds said more. So no one will ever say, we are claiming the moon, because the treaty forbids it. But whoever installs solar farms on the sunniest ridge, whoever builds roads besides the ice pits, will quietly control the most strategic ground. Not the whole moon, just the irreplaceable golden plots that enables power, water, fuel, and expansion. These locations are scarce, and they determined who can stay longest, operating cheapest, and scale fastest.